recording. Please hold on, sir.
Okay, madam. Okay.
Good afternoon, everyone. Today we have our speaker, Dr. B. Surendran, currently working as Associate Dean Academics in National Institute of Technology, Puducherry, Karaikal. Dr. B. Surendran has more than 15 years of experience in teaching and has published 30 plus papers in reputed national, international journals as well as conferences. He had reviewed more than 280 papers for various journals and conferences. Dr. B. Surendran has delivered many guest lectures, especially during this lockdown. Sir has delivered 30 plus guest lectures. Dr. B. Surendran received Best Reviewer Award in the year 2019. Dr. B. Surendran is an expert in medical imaging, image and video processing, data mining, dimensionality reduction. So now I request Professor to handle the session on dimensionality reduction.
Thank you. Thank you for inviting me for this lecture. And so, myself, Dr. B. Surendran from NIT Puducherry. I did my PhD from NIT Trichy. And today we'll be discussing about dimensional reduction methods, various types of dimensional reduction methods. Is my voice audible?
Yes, sir.
Okay, madam. Just a minute. Yeah. So today's session I'll be covering all this contents. So it's a wide dimensional reduction. What are dimensional reduction methods? Various methods like filter and wrapper based methods, feature extraction methods, and I'll be talking about CAB ratio. That is another different parameter which you can use it as evaluating with several algorithms, comparing with several algorithms, which is people are not much aware of that. And I will also explain about my research work I did it at NIT Trichy for mammogram analysis, where I applied several new features, extracted new features, and we applied various dimensional reduction methods. So when we talk about data dimensionality, so whenever when we have some data, so we'll be even if you have an image, okay, we'll be extracting features, and then we'll be going for classification using SVM, ANN, or any other classifiers. But nowadays people are using deep learning, but previously, they used traditional classifiers. And in some data sets will not have the images. We'll be having the actual data, numerical data, and other data. So for that, we'll be using these classifiers. And here, so what happens is, when we have the more data, so the classification takes more time, the complexity increases, and another thing is it takes more, it leads to worse performance. That is, let me use a pen here. Yeah, so inclusion of more features leads to worse performance of the classification. So that is called as, we call it as curse of dimensionality. So if the number of training samples increases, or if you use more features, then the training takes more time, and it increases exponentially with more dimensions. Okay, so we need to have lesser number of dimensions. That is our objective, so that we get a better classification, accuracy, and all other performance. So that's why we go for delta dimensionality methods. And here, how to achieve dimensionality reduction? Okay, let us say we have n features. Let us say we have a data set, and we extracted some features from the data, for that maybe some image, maybe for any cancer image, we extracted some texture features like that. So if you let us say we have n features here, and we have to reduce it to k features. The features may be like from the images, like texture features, GLSM features, or any other features which we extracted from the images. So we have to reduce from n to k. K is less than the n value. And yeah, so here you can do with linear or nonlinear transformations. And here you can use a feature selection algorithm or feature extraction algorithm. So in feature selection, that is, let us take, this is a full feature set, this is actual feature set. These are several features. Totally we have, I think, around 9 features are here. Okay, so here 9 features, different colors are different features, and in this we have to identify the useful feature. So which feature is only useful for us? So finally we selected these 3 features are useful. This one, and this one. 3 features are useful. Remaining features are not useful for classification or for our the current data set for any for classification. So we use only 3 features. So this is a feature selection algorithm. We select only the 3 features from the original 9 features. So from 9 it was reduced to 3. So that is using feature selection algorithms. So this is the dimensionality reduction. Okay. There is another way, that is it's selecting a subset of the features. There is another way, we call it as using a PCA or independent component analysis. So many other methods are there where we use feature extraction. Okay, so I'll be discussing about that. So where combination detection methods are used, where we have applications. So we have vast number of applications. So especially in mostly in some handwritten digit recognition. So and implicit detection methods, where we have several features from the networks. I mean, network related features like the TTL and all those several parameters. So from that we have to identify the best features. And similarly for image retrieval, text mining, and other places, it has vast number of applications. So when we reduce the number of features, the complexity of the classifier reduces, and we have better performance. And the training time also takes less time. So that is advantage of using lesser time dimensions. And here you can reduce from, let us say, 100 features if we have in your data set, you can reduce it to 10 features or 20 features, like that. So the number of features finally we'll be using it only 10 or 20 features. That will reduce, that will increase the performance of the classifier. And as already said, feature selection algorithm, there is another method called as feature extraction. So these are the 2 major techniques in dimension detection methods. So feature selection and feature extraction. So in feature extraction, we have PCA, independent component analysis, LDA, and so many other methods are there, and image factoring, factor analysis. These are the various methods available under feature extraction. So what is meant by the difference between the feature selection and feature extraction is, in feature selection, we'll be selecting optimal subset. Okay, so from n features we select k features. Out of n we select k features. So that is the feature selection algorithm. And here it is simple to implement, and I mean it is speed of learning is better here. It improves the performance of your classification algorithm. And in feature extraction method, that is based on like PCA, independent component analysis, or factoring analysis. So here what will happen is, we have given a set of points. Okay, so we have n features. Let us say we have n features. We use the combination of n features, each and every we multiply x1. x1 is first feature, x2 is the second feature, xn is the nth feature. So we multiply x1 into some factor value or some weight value, plus or minus, we'll be using some combinations, and we multiply x2 with another weight value, like that we'll be multiplying, and we'll be getting, we multiply all the values and we create a new feature. So that is, we call it as a PCA. So here we call it as a components, using, they calculate using eigenvalues and eigenvector. And so we can extract n number of components. So if we have n features, we can extract n number of components, but we can select with 4 to 7 to 10 or any number of components we can select. Based on our requirement, we can select the minimum number of components for classification. So that way we can, it will not the extracted features, the outcome of these features, okay. 4 to, let us say we have 4 to 7 components we are using it. In this case, these are all the combinations of all the existing features. So no same feature will be used here in the out of 4 to 7. It will be a linear combinations, or not the exact features will not be used here. This new set of features will be used in the feature extraction methods. So that is about the feature extraction. Yeah. So feature selection, I already said, it's a subset of features. And in feature extraction, so here we'll be using a linear combination of the original features. The transform features are nothing but the linear combination of the original features. So here, how the dimension detection methods will work. I mean, how the various algorithms are grouped into different categories, or what are the factors or the evaluation measures they use. So here, the algorithms are grouped under in feature selection algorithm. We have filter and wrapper based method. So we have feature extraction and feature selection algorithms and a dimension detection. And feature extraction, we have PCA, image factoring, factor analysis, and other methods. In feature selection, we have two models, that is called as filter model and wrapper model. So what is filter and wrapper model? I will be discussing in the next few slides. And here we'll be having a searching algorithm and feature ranking algorithm. So here we have a search algorithm to identify the best subset of features, and we will be having some ranking based algorithms, so that will rank the best set of features. And the features are selected using various evaluation measures. So here, how the best feature is selected is based on some evaluation measures. So what are the evaluation measures? We'll be discussing it in the next few slides. And later, the selected feature set will be evaluated, and it will be final optimal subset will be selected in the feature selection algorithm. The best optimal subset algorithm, subset of features will be selected. So let us take this is a search space. So this is search space for 4 attributes. Let us say you have a data set containing 4 attributes. Let us take A. Let me clear it once. Yeah. So let us say we have A, B, C, and D. These are the 4 features in our data set, and we need to identify among these 4 which one is the best subset. It can be A alone, or it can be a B alone, or it can be C alone, or it can be D alone, or it may be a combination of A and C, or B and D, or A and B. It can be 2, or it may be 3. 3 features may be a best subset. So we don't know which one is the best subset. How the algorithm will work is it will construct the search space. So this is the combination of various search space. Huh? Orange. Sorry, someone came here. Yeah. So here we have 4 features. We have to select the best subset. So how this will work here? If you consider here, we have 4 features. Initially, this is the maximum search space. Okay. Here we have none of the features are selected here. Here we have all the 4 A, B, C, D. All the 4 features will be selected here. So how the system will start is, it will start with, it can be any order. It can start with empty set, or it can start with full set. Okay. So let us take the one of the, I mean, let us take any algorithm. It will finds the first one. Let us say that it will select only one set of the features. So here we have only A here. It selects A and it checks whether it is performing best. Here we have only the feature B. Here is only the feature C, and here we have only the feature D. So now, from these four combinations, four different subset, it will identify which one is giving the best one. So let us say that B is giving the best subset. Okay. So let us say we have B is giving the best subset and remaining things are not giving the best result. Okay. So then what the algorithm will do, it will check the next best combination. We selected B here, then it will combine with combination of B with A, B with C, B with D. So here we have AB, and here we have BC, and here we have B and D. So these three possibilities are there. So from these three, which one is giving the best subset? It will identify the best subset among these three. So let us say it selected B and D. B and D is giving the best subset. Okay, compared to AB and BC, now we have only the best one among these and CD. Sorry, AB and BC and BD. So among these three, we have B and D is giving the best one. So next, with the B and D is over, now it will take the third combination. It will add either A and B to check which is the best one. So here we have, this is the one combination and this is the another combination. So now we have ABD and BCD. Among these three, let us take BCD is giving the best one. Then later it will go to the final one, that is all the four features will be added. So this is how the search algorithm, it will start with empty, it will add one by one first feature, then it will select the second best, then it will select the third best, then it will go to the all the four features, it will reaches the end. So now this is how the search space is used for identify the best subset of features for the various feature selection algorithms. So here we moved from top to bottom. There is a forward direction, that is sequential forward. We moved from forward direction. This is a forward, and there is another way that is called as a backward elimination. Okay, so this is a backward elimination. Okay, so here we start with the full set and we'll remove one by one, then we'll reach the empty set. So that's a backward elimination. So this is the set space, how it works. Here for the searching algorithm, so we have different aspects here. So one is the starting point. Either you can start with empty set or a full set or random point. That is, yeah. Here you can start with either empty set or a full set, or you can start with any random point. You can start and you can add or delete the features. Okay. So that is the starting point. Another one is the search direction. So here we have sequential forward selection. That is the example I shown here. From top to bottom, we will be selecting one by one. That is a sequential forward selection. Okay. Another one is sequential backward elimination. We select all the four features and we remove one by one, and we'll be going to the empty set. That is a sequential backward elimination. Bidirectional generation is you will be doing it in both the directions. That is a bidirectional generation. Okay. And random generation is we'll randomly generate the next subset. We'll randomly add or delete the features. So that way we identify the best subset. So here this is sequential forward. Let me clear all. Yeah. So this is a sequential forward and this is a sequential backward elimination. And random generation is, let us take some random point. Either you can delete or you can add in features to this set. So this way you can randomly from an point you can do the random generation. So that is how the searching algorithm works, searching directions and all these aspects of the search algorithms. And here, when we have four features, this is the search space for the 4 features. Let us say we have 20 features or maybe 100 features. Then the search spaces will be very, very large, and searching the full search space is a very tedious task. It's time consuming. So for that we have heuristics algorithms and non-deterministic search algorithms. Different algorithms are there. So in the exhaustive complete search, full search space will be used to identify the best subset of features. It will extract all the combinations of all the features, and from the full set it will select the best subset. And heuristic search and non-deterministic search, it's a different ways of searching the best subset of features. And here for all these algorithms, so here is a sequential forward generation and sequential backward generation algorithm, bidirectional generation and random generation. How it is mapped to complete heuristic and non-deterministic. Okay, so this is the how the searching algorithm, feature selection algorithms, how the search direction and strategies work for the feature selection algorithms. And it also uses either a depth first search or a breadth first search. Either you can use a depth first or a breadth first search. It's up to the, I mean, based on different algorithms, they deploy, I mean, they use depth first or breadth first search. Here, yeah. And in this feature selection algorithm, so we have another type of algorithms called as in a filter. We have a filter and wrapper based methods comes under feature selection. In filter, we have we can identify the best subset, and also it has a ranking algorithm. So in feature subset identification algorithm, let us say we have 10 features, and it will select maybe 3 features is best. Okay, it will eliminate the remaining 7 features out of 10. In feature subset selection algorithm in the filter based methods. So we have, let us say we have 10 features. It will select, let us say 3 features, and this is the best subset. Okay, in filter based method, feature subset selection methods. And there is a in filter based method, this is also the ranking also comes under filter. So filter based method, we have feature ranking algorithms, and what the feature ranking algorithm does is it will not select the best subset. It will rank all the features in the priority order, and we have to identify the best subset. So that is a feature ranking algorithm. It will rank all the features based on their best one. Okay. So for how long PPT is not there?
From the slide.
Now it's visible, sir.
From this feature ranking slide only.
Okay, okay, fine.
Thank you, sir.
Yeah. So in yeah, now here in feature ranking, so will be it will rank all the features. It will rank all the features. It will not select the best subset. We have to select the best subset. And here, what is the threshold? What is the best subset? We have to determine ourselves. That is the disadvantage of this ranking algorithms. And it is easy to implement. It ranks. I mean, the feature ranking algorithm performs faster. Okay. And what are the evaluation measures we use it here? So the various feature ranking, feature selection algorithms, they use different measures for identifying the best subset. There are information measures, distance measures, competency measures, consistency, and accuracy measures. Okay, I said in feature selection we have filter and wrapper based method. In feature selection we have filter and wrapper based method, and filter we have feature subset selection, and feature ranking methods. So in filter we have feature subset selection and feature ranking, and we have a wrapper based method. So in the wrapper based method is nothing but it uses a classifier. Wrapper based method uses a classifier, but filter based method will not use any classifier. The other independent algorithm, filter based methods, and wrapper based method uses a classifier. So here the accuracy measures will be used by wrapper based methods, mostly used by wrapper based methods. And we have distance measures like Euclidean distance and other distance measures are used for finding the best subset. And information measures are nothing but like in decision tree we use entropy information gain. So those measures are comes under information measure. These also used to identify the best subset of features. And we have consistency and dependency measures. I'll talk about that. So yeah. So consistency is, I'll show you next slide. Let us say we have two instances, I4 and I8. Okay. So here this is a sample data set. So here we have 8 elements, and here these are the 4 features here, and this is the class. Okay, that is the result, whether it is 0 or 1. In this case, if you see I4 and I8, so here we have the values. You can see the hair, height, the weight almost looks similar except lotion, but you can see the class variable. So class here is 1, here the class is 0. There is an inconsistency with the data. So this is called as inconsistency measure. It will try to identify which are the values are consistent, which are not inconsistent. So based on that, it will use it to identify the best subset of features. So that is a consistency measure. Okay, and yeah, difference measure is a correlation. They use a correlation. So those measures will be used for consistency measures. Sorry, dependency measures, and yeah, accuracy measures used by classification. Used by the classifiers as a evaluation measure. It's mostly used by wrapper-based methods. So that is the accuracy measure is used here. So as I already said, we have filter-based method and wrapper-based method for feature selection. And here, in filter-based method, they use information measure, distance, dependency, and consistency measure. And the wrapper-based method uses accuracy as one of the measure here. And the filter-based methods have advantages because it is no bias towards any learning algorithm. So because we don't use any classifier here, so it is independent of the classifier. So it is a fast to compute. Okay. And in the wrapper-based method, we'll be using a classifier. So maybe you can use an AV bias or ANN or SVM, any one of the classifier for the wrapper-based method. So it tends to be the selected features will be not generic like filter-based methods, even though we'll get a best subset of features which is dependent on the classification algorithm. So in a filter-based method, so we'll give all the features. Okay, let us say we give a 10 features and we select, let us say 3 features. So this is the output. Okay, so here, so we'll give a 10 features. Let me clear it. Yeah, let us say we give a 10 features. So from the features, we will select the subset here. It uses evaluation measure here. We have different any of the evaluation measures like consistency or distance measures or these measures, and to identify whether the selected subset is enough or is the best one. If it is best, then if it is the best subset, then it will apply to the classifier. This learning algorithm is a classifier. It will line with the best subset and apply the classifier. Then we have the accuracy. Okay, the subset, best subset may be 3 features. But if the selected features is not best one, then it will again select the another subset of features. So like way it will execute and it will come out only if you have a best subset of features. And there is no other feature which even if you add after 3, there is a no best result you will be getting it. Then it will stop at the 3 features. So this is how a filter based method will work. And here in the measuring, we have the distance measures or the evaluation measures will be used. Different algorithms are used here for identifying the. This is the method we used in the filter model. In wrapper-based method, so wrapper-based method is based on the classifier. So let us say we use a 10 features as input, and from that we will select one of the subset of the feature. And here learning algorithm is the classifier. So here we use the classifier. Okay, so classifier is used here, and based on the accuracy, it will identify them for the subset. It will identify whether the any more subset is is good or best subset. It will identify if it is a best subset, then it will apply for another classification algorithm. Then we'll get the accuracy. Otherwise, it will identify the next subset of best subset of features. So this is a wrapper-based model. Here the difference is it uses a classifier as the learning algorithm. So for demonstration, I'll be using a Beaker tool with iris dataset. So here in iris dataset, iris is a flower dataset. Okay, so iris flower dataset, it contains 3 types of flowers. That is iris versicolor, iris setosa, and iris virginica. These are 3 types of flowers under iris type. So here it has 4 features. That is sepal. This is a sepal, and this is the petal. So they have 4 features. That the 4 features are sepal length, sepal width, petal length, and petal width. So sepal is this is a sepal, and this is the petal. The smaller one which comes here. This is the petal, and sepal length and width, petal length and width are used as a 4 features to differentiate between the 3 flowers. So here we have 3 classes. So since we are going to group them into any one of these 3 classes, and we have 4 features: petal length, petal width, sepal length, and sepal width, or 4 variables or features. Under each category, we have 50 images or 50 data are available for each and every flower. Totally, we have 150 instances or cases. And since we have 3 classes, it is a multivariate classification. So if we use only 0 or 1, if the class output is cancer or normal or 0 or 1. So in this case, it will be a binary classifier, binary classes, 2 classes, or bivariate. And if we have more than 2 classes, we call it as a multivariate. So here we have 3 classes, we call it as a multivariate. So what we do is, in the classification algorithm, we'll be giving the 4 features along with the class. That totally 5 features will be given for classification, and we try to classify based on these 4 features whether we are able to classify the flower as versicolor, setosa, or virginica. So that is our objective. The accuracy based what we get is how much accuracy, how the features are effective, and how the algorithm, classification algorithm, is able to learn from the features and give the better result. So in feature selection algorithm also we'll identify among these 4 features which is giving the best subset of which subset of features is giving the best result. Which features is enough for classification. For a small data set, the increase in accuracy with the lesser subset of features will not be much different. There won't be much difference. But if we use 100 features, let us say we have original data set contains 100 features, and if we select 20 features or 10 features, let us say we selected 12 features. After feature selection, we used only 12 features. So let us say 100 features. From that, we selected only 12 features. The accuracy we get from here may be, let us say, 89, okay, 89% accuracy. But in case of 12 features, the accuracy may increase to 93%. So there may be a increase in accuracy if you use a lesser number of features. It may not be the case in all the time. For a small number of features, there won't be any much difference. But there are possibility that if you use a lesser number of features, the accuracy may increase. So I will show the demonstration after the remaining slides. At the end of that, I will show the demonstration. So another important factor or measure which I like to share here is the CVB ratio. So what is meant by CVB ratio? Which people are not aware of that. And when I did my research, when I was about to write, I mean the last 6 months before my thesis, I came to know about this CVB ratio. So which is called as cases to variable ratio. So what is meant by cases to variable ratio? Let us say in iris data set, we have number of cases is 150 cases, that is 150 instances cases. Number of features is 4 features, excluding the class variable. So 150 by 4 is the CVB ratio. So for each and every image, iris image, we are extracting only 4 features. So that means that CVB ratio will give you a higher value. Okay. In this example, I given here the data set. It contains 10 features here, 10 cases or 10 instances, or from 10 different images or anything. They extracted 2 features. We have 2 features here. We have 1 class variable. So for this data set, the CVB ratio is 10 by 2. So 10 instances here. We have 10 instances or 10 cases. Divided by number of features is 1 feature, 2 features. So 10 by 2 is 5. So this is the CVB ratio. Why it is important? Okay. So if you see some of the data set they used in the literature, in the initial stages, like using wavelets or texture features, GLCM, or these features, LBB, or any other set of features, they extracted large number of features. It's like for each and every image, they extracted 300 wavelet components or coefficients, wavelet coefficients, or GLSM features maybe around 80 or 240 features. So like that. So in that case, the number of images they used also less, but the number of features is very, very large, which may overfit the classifier. Okay. So that is not effective. If you use a large number of features, it will not be effective in classification algorithm. Okay, why it is not effective is, for the data set it may work. If you add some new data to the data set, then it may not effective to it will not effectively classify. Okay, it will overfit the classifier. So in that case, we have to consider the CVB ratio as one of the parameter to evaluate the various literature works you can compare. Even though they shown that better accuracy, but their CVB ratio may be very, very less. So what is the optimal value we should have? Whether higher value CVB ratio is good or lower CVB value is good. So higher value is good. It should be higher than 4.16. It is mathematically proven a value CVB ratio that it should be greater than 4.16 or 4.26. So it should be greater than this value. Then the feature set what you are using for classification is best one. The features we extracted for the data set is optimal or the best one. If it is lesser than this, then your feature set is not effective, and it may overfit the classifier. That is what you can infer from that. So I will come to this MATLAB region props. One minute. Okay. So when I did my research at NIT, I did a mammogram analysis. So here, when I started my research work in 2007, So I am also not into image processing and all those things, and it's everything is new for me, image processing and all those things. So I started learning from basics. And here in memograms, if you see, a lot of works have been done for more than 20 years, 15 to 20 years. So when I started working with that, I faced a lot of difficulty to identify the, research where to focus and which one to be considered like that. So I'll tell you how I moved my research from starting to how I moved to the proposed new set of features and all those things. So here in the mammogram, the tumors are called as a masses. We call it as there are two types, that is benign and malignant. So benign is the early stage of the cancer, it will be smaller in size, and malignant is advanced stage of the cancer, it will be bigger in size. You can see this is a tumor size, so it's a bigger in size, it's a malignant cancer. Okay, it's a X-ray image, we call it as a mammogram. So mammogram is nothing but X-ray image of a breast is called as a mammogram. And here, so the abnormalities or tumors we call it as a classification and masses. And why digital mammogram we have to use it is because it's very cost effective, and frequently you can take the mammograms, and easy to, in the starting stages it will be easy to interrupt. And for this mammograms, they use a standard called as Bayer standard. So it's a standard used by the radiologists to identify how they identify the masses, okay, or the tumors, how they identify. It will be, their masses are characterized by their shape, size, margin, or nothing but borders, and density. So these are the various features they use to identify whether the tumor is there or not. If the tumor is there, whether it is benign or malignant can be identified based on these four parameters. Okay. And if we take the mass shapes, the shapes are in oval, round, lobular, and irregular in shape. That is the, I'll show the next slide, it will be better. Yeah. So if you see the mass shape, it can be in a round in shape, it can be oval in shape, lobular, or irregular in shape. And the margins or the borders, if you see, it will be in a different combination, circumscribed, obscured, or microlobulated or spicullated. And most of the literature works, they consider normal with cancer. They combine benign and malignant into a single group like cancer. They classified between these two. Some works they classified as benign and malignant. Okay, but there is a catch here. What they did was, actually the benign, most of the benigns will be into this group, benign, and the malignant will be here in this group. Sorry, this is malignant. Yeah, this is a malignant. Advanced stages of the cancer. So, but there are some images like oval and globular, both can be benign or malignant. Okay, so benign may be in a lobular shape, malignant may be also maybe in oval shape, but these two are difficult to classify because benign also can be in oval, malignant also can be in oval. Benign or some benign may be in a lobular shape, malignant also will be lobular shape. Sort of the most of the research work they did, they not consider lobular shape for classification. Mostly they avoided lobular and they used the remaining for classification. So what we did was we took why not we identify some new features so that we can able to differentiate based on the shape and we can give a better accuracy. So for this we used Myers and DDDSM data sets, and we used all the type of cancer images, that is cancer or malignant, benign, and normal cases we used. And why I used CVP ratio is, if you see the mammogram analysis, what they worked, if you see the literature works for 320 mammogram cases or patient 322 patients, for each and every image, patient image, they extracted 300 coefficients. For each image, they used 300 features. And in another work, for 144 cancer patients and images, for each and every image, they extracted 280 features. Like this, they have several more number of features. So here you can see 142 patients. For each and every image, they extracted 400 coefficients. So in this case, it will surely overfit the classifier. It may not be effective. And the CVP ratio, if you calculate here, CVP ratio if you calculate here, it is very, very low value. It should be greater than 4.16. So we decided to identify the best subset of feature, or which feature will be effective for classifying these mammogram images. So that is our objective. We thought this can be our main objective. I mean, we started with some statistical features, then we moved into geometric features. Yeah, first one we started with statistical measures. So for this we use HSV color space. HSV here we have hue, that is a color, and we have the saturation, and we have the brightness or more brightness, that is a value. Okay, so HSV color space is better one because this is how the humans visualize the objects. How we visualize this, we identify based on the color, then it will identify the how much the brightness and saturation, and then it will be able to differentiate the objects. So this is how the human visualize visual perception, call it as a human visual perception. So it's related to human visual perception of color and gray pixels. This is most related to HSV color space is most related to how human visualize. So this color space we consider. Just a minute, I'm getting a call. Hello. Yes. Yeah. So what we did was it's HSV color space is for the color images, but in case of mammogram, if you see, it will be in a gray image. If you see the mammograms, it is a gray color image. So here, if you use a gray color image, the gray color will be R equal to G is equal to B. That is the value we'll get if all the values are equal, R equal to G equal to B, then we call it as a gray color image. So, but however, we used for the mammogram images, we used HSV RGB to HSV colors space converter. This is a standard formula available for converting from RGB to HSV, and we used a gray weight function. It is proposed by my guide Dr. A. Badibe during his research. It is a new feature which is not there in the literature. Okay, so the gray weight function uses S and I, not the H. The color value is not considered here, and it is for not R equal to G equal to B. So what we did was we slightly increased one of the RGB light variation, and we calculated this one. And we have to identify the R1 and R2. It's usually it will be a 0.1 and 0.85. It was this parameters values, and using this gray weight function, we can able to range the values from 0 to 1. It will use the level of grayness in the image. Okay, it will gives you the level of grayness of the image for each and every pixel. So for each and every pixel, this will be calculated. So we will get the values for each and every pixel. Usually it will be 0 to 256, so 255. So it will be converted into 0 to 1. For each and every pixel, it will be a gray weight function. So we used this gray weight function. It was applied for content-based image retrieval, CBIR. It was found to be very effective. So we used this one. Initially, we started with memograms, and we applied this here. And we started with the k-means clustering. We applied with k equal to 2, 4, 6, and we have 8 clusters. But even if you go for 8 clusters, it will come up with only 3 or 4 clusters. It will not go for a higher number of clusters. And after the clustering results, so this is one of the result. So this is the original image, and this is the clustering result. So what happens is here, this is our tumor region, which is not clearly segmented. So what we did was, we used connector component analysis to group the similar nearby elements, and finally we got the output like this. After several levels of connector component analysis, some 2 to 3 levels, then you will get a clear picture like this. So from this, we identify the region size. Based on that, we'll identify the tumor area. And from the tumor area, we applied gray weight function. And for each gray weight function, we extracted statistical measures. So these are the statistical measures we extracted using a gray weight function. Gray weight value of the pixel, we used that for calculating these statistical measures. And we applied for 40 mammogram images, 20 benign and 20 malignant. What happens was, the statistical measures are found to be effective in the initial stage for lesser number of mammogram images, and it was able to discriminate benign from the malignant images. We classified as benign versus malignant. And these are the some of the mass region extracted and what is the statistical features values. Okay, so here we classified the mammograms into benign and malignant. So benign and malignant we classified, and you can see it is able to differentiate the both the colors. You can able for each and every features we are able to discriminate both the types, that is benign and malignant, for 40 images. But what happens was, when we increase the number of images, so we started with experiment with 40 images, then we moved to 350 images. In that case, it was not effective. The statistical measures are not good in discriminating the masses, or it's not able to discriminate benign and malignant. Then we explored why it is not able to discriminate, and also I attended one workshop in Triveti, Hyderabad. So there I came to attend a guest lecture by a foreign professor, and they worked on mammogram using geometric features. So that was a motivation for my research, and we moved into geometric shape-based features for mammogram classification. So for this, we used the mass characteristics, shape and mass characteristics. So we saw that this is a Bayreuth standard. This is a standard in a best imaging book. Also, they specified this is the standard how the masses can be grouped, okay, or discriminated. These things can be benign. These things can be malignant. So this is a way, the standard they follow to discriminate the masses. So we thought how we can use this shape characteristics to classify the masses or mammograms. And what we did was, the most of the literature work, they not consider the lobular types, and also some of the time they not consider the oval types. So in our research work, and also some of the time they not consider irregular also. So what happens is, in our research work, we used maximum number of lobular, irregular, and oval shape mammograms, and we used them for classification. This is the number of for 300 images, mammogram images. So this is the how many number of irregular masses are there, how many oval, 66 oval masses are there. So like that, we this distribution of masses. And we moved into geometric shape-based features. We extracted some new geometric shape-based features. How we extracted these features, how we introduced some new features also for mammogram classification. So here, how we, yeah, these are the new features. So if you see here, which is mentioned in the bold, so modified circularity, C1, C2, dispersion, modified eccentricity, and elongatedness, shape index. These are all not the existing formula. So initially they used a radius as a measure. Here we used a max radius. So what we did was, uh, here also they used, actually original formula was radius by area here for dispersion. Okay, so what we did was we tried different combinations and we tried to identify the best feature that can able to discriminate the shapes. So how we found out this combination is using a basic shape structures we identified. So what we did was we started with the basic shapes. So we constructed some template with the different shape structures, and we tried to use a different combination of the features, existing features as well as the modified features area, because what we found was most of the features they use only the radius, the average radius or the minimum radius. Okay, so what we found was in some of the cases, if we take a rectangle, if we find the center point, the min radius, this is maybe the min radius, this may be the maximum radius. Okay, so this way we can able to somehow we can differentiate using mathematical techniques the shapes and
I couldn't hear you.
I think it got disconnected. Let me. Yes. So here the shape features are position and rotation invariant. Okay, so these are the various features, and we extracted from the for the mammogram masses. And you see here the circularity 1, which is always gives a value 1 for round masses and 0.5 for perfect squares. Similarly, elongatedness, it gives a 0.78 for round masses, always gives a 0.78, and 0.25 for perfect squares. So like this, these several features, it have specific values for specific type of shapes. So this is what our from an inference using a modified features, and we used that one for the mammograms. So how we implemented for mammograms is we used MATLAB function region props. So that is a function, that is a region props is inbuilt function is available. Okay, so we used that to extract some of the shape based features, and also we used Java programming, Java to extract the additional features, because we applied k-means clustering and as well as contact component analysis. Then we extracted the some of the features from the mass shapes. And yeah, I will come to this. So here So we compared with the Harley texture features, that is we extracted 76 features, it gives 84%, but they proposed only 17 features, it gives 86.7%. And if we take the CVB ratio, 300 images we taken, 300 by 17, it will gives around more than 70. The value is 17 point something. Okay, it's greater than 4.16. So that means the CVB ratio also very good. So that's about the shape-based features. This is how we have done the mammogram analysis, and for this we applied feature dimensional detection methods. So here we used PCA components. We extracted for 17 features. We extracted PCA components. So for 17 features, it will extract 17 components. So from this, we selected the best. We started with 4 components. So after that, it won't be giving any much difference in accuracy. Okay, so here we applied feature selection algorithm. We call it a stepwise ANOVA. We applied. We used SPSS for this, which is not this stepwise ANOVA is not available with other tools. It is available with SPSS. So we used this stepwise ANOVA as a feature selection algorithm. We selected 5 features and we got an accuracy of 87.3%. Out of 17 features, 5 are selected. So from initially for 17 features, we got 86.7. But if we see after feature selection, 5 features, accuracy was increased to 87.3. And we also compared with the PC and image factoring, that is 4 factors and 4 components, the accuracy is less. Okay, so what are the 5 features we selected here? These are the 5 features, that is optimal subset of features out of the 17 features. Standard deviation, I think entropy, dispersion, and Euler number, and all those things. So this is the performance comparison. So yeah, that's all about the presentation. I'll go into the VCAR tool. I'll show a demonstration with the VCAR tool. So for this, I'll be using iris dataset. So I'll show that once again. Yeah, for iris flower dataset, we'll be using 3 classes: iris versicolor, setosa, and iris virginica, and we have 4 features. So it is petal length, petal width, sepal length, and sepal width. And I said the region props. So region props is a inbuilt function in MATLAB. So it will give you these 24, I think, set of features from the for each whatever the region you are going to give. Okay, so let me show the demonstration. I'll stop sharing and I'll share my full screen. Yeah. Is my screen visible?
Yes, sir. Visible,
Yes,
sir.
sir.
Okay, so I have opened the VCAR Explorer, VCAR tool. So here it's very easy to use. Now, no coding is required, no coding knowledge is not required for this, and it's a free open source, and it has several more than 45 classification algorithms are there present with this tool, and it uses a format called ARFF for the data. I mean, inputting the data, And also you can use CSV format. If we have Excel format, you have to save it as a CSV, then you have to add it in the Vika tool. So for that, if you want to convert them into different formats, you can use tools ARF viewer. Otherwise, you can, if you have CSV file directly, you can use that for your classification and other methods. It has several interfaces, so all the interfaces will have all the functionality. But the thing is, command CLI is like command line interface using commands, and knowledge flow is another way of representing your work. I mean, doing the algorithms and all those things, playing algorithms. So you can use Explorer for, as a default one. So, clicking on Explorer here. Shall I magnify or it is visible? I couldn't see the comments because I am in full video slide. Anybody can tell me the, yeah, okay. So here in Vika Explorer, we have several tabs. Okay, so we have pre-process, classification, clustering, association rule mining, select attributes, and visualize. So what the select attributes, the feature selection, filter, and wrapper based methods, everything comes under select attributes. And the pre-processing, where you have the various filters and all those things, and classification algorithms comes under classify. Now we have to open the input data. So we use iris flower data set. Let me click open file. Let me go to C drive and program files. Okay, program. So Vika folder, you have data. So they gave, I think, several data sets for experimentation. These are the existing data sets available along with Vika tool. You can use them for learning. There are a lot of tutorials are also available in the net. So where they used these data sets for explaining the various algorithms. So let me use iris data flow, iris data set. Okay, so now we have, it has, you can see it has 4 features and 1 class variable: sepal length, sepal width, pedal length, pedal width, and class variable. Talk to me. Talk to me. நான் கால் பண்றேன். So here we have 3 types of classes, that is iris setosa, versicolor, and virginica, each containing 50 counts. So this is the how the data is distributed. So if you click on each and everything, you can see the distribution about the data. So now let us try applying feature selection algorithm. So another 5 minutes. So first we will apply classification algorithm, then we apply feature selection, then again we apply classification. So we will try to see before feature selection, after feature selection, what is the difference in accuracy. So let us go to classify. So here using the classified in default it shows 0R. So let me choose, click choose. You can see different classification algorithms grouped into different categories. So navy bias comes under the base. Functions we have multi-layer perception is neural network and other algorithms. And we have lazy learners and meta adapt boosting bagging algorithms comes under meta. And we have trees like decision tree J48 is C4 C5.1, and these are the various decision tree algorithms are here. Let us apply navy bias. Okay, another thing is here is you can use percentage split. So if you say 70, that means 70% training, 30% testing, or you can use cross validation, 10-fold cross validation or 5-fold cross validation, you can specify. So let us go with the percentage split 70 30 percentage. And here you have to check what you have to check is you have to choose the class variable. So default to be the last variable will be the class variable. But if it is not the last variable of the class variable, then you have to specifically select the class variable here. It will click on class variable. And here, if you want to change the parameters for the algorithm, you have to click here, the Navy Bayes algorithm. So here, if you click, it will open the window where you can specify the parameters for the algorithms. Okay, let us leave it everything as default. Okay, so now since we set a Navy Bayes here and we given 70-30 as a percentage split, usually for classification they use 60-40, 70-30 or 80-20. This is a normal training testing ratio used by the researchers. So when we submit a paper for a journal, so sometimes what happens is some papers I have seen they will write only the training results. Okay, that is not the correct one. So you have to use the training and testing results. Testing results only you have to show. So here, after selecting the algorithm, let us give start here. So it gives the accuracy. This is the correctly classified instances. So 95% accuracy. So let us see here. So here the ID data set 150 instances, 5 attributes. It is including a class variable, and the percentage split is 70% training, remainder is a testing, and we got accuracy as 95.556%. This is accuracy, and these are the other metrics available along with this tool. And here we have the misclassification. Wrongly classified is 4.44%. So now let us go to select attributes and we apply feature selection algorithm. Okay, so now we have various evaluation algorithms available with the Vika tool. So let me show you the list of algorithms. So these are the list of algorithms are available here. You can see wrapper based method in the last. This is the wrapper is a classifier based one. And there is also one more classifier based, classifier subset evaluation. So this is also classifier based wrapper based method, and one early FAF, I think info gain and all ranker based methods. It rank the features, it will not select the best subset. So and CFS subset and classifier attribute evaluation, this algorithm will select the best subset. Let us use CFS subset evaluation. So if you want to know about this algorithm, so each algorithm will use a separate search method. Okay, so each method will use their own search method. So it automatically chooses the best search method for that algorithm. If you want, you can also change the search method here. And here for CFS subset evaluation, you want to know about this algorithm, click on here, it will open a window where under more you can see what is the source paper from where they taken the algorithm and all those things. So that will be giving, then we will be getting those information. And here you can also change the parameters. Let us not change anything as of now. If you can learn about that in the options here, what is each and every parameter and all those things. And let us leave it as such. Okay, let me minimize this. So here we have the class variable is there. So in the data set, I choose the class variable name here, and let us click start. So it selected two features are the best one. Let me zoom in. Yeah. So here we have two features, pedal length and pedal width are the best subset of features. So we have 4 features. So sepal length, sepal width, pedal length and pedal width, and one class variable. 1 minute. Hello. Sir, I am in a lecture. I will call you back. Yeah. So among these 4 features, pedal length and pedal width are selected as a best feature. Okay. So So another 2 minutes, I'll finish it off. So now we have to select only these two features and we have to apply for the classification. Let us go to pre-process. We have to select only pedal length and pedal width. We remove sepal length and sepal width. We remove. We select these two, and these two are not required. We remove them. Okay. Zoom out. Yeah. Remove here. So now we have only two features and one class variable. Again, we go to classify and we use the same setting, navy bias 70/30. Let us click start. Now we have only three features, one class variable, and let's click start here. So it gives 95.55%. But here in the previous case also 95.55, now also 95.55. There is no decrease in accuracy or increase in accuracy because the data set what we used is a small data set with only 4 features. But in some cases the accuracy will increase. Okay, and let me undo it, and I'll show you with the rank-based method. So now we have all the 5 features. Let me choose ranker-based method. Let me use relief of attribute. It shows the rank search method. You have to choose some other search method. You click yes. So now we used relief of attribute as a method, and it uses a ranker as a search method. So we have to choose the class. Since it dataset contains class variable, we choose the class variable. Otherwise, it will use as a class also as one of the feature. So let us click start. So here you can see, let me use a magnify. You can see here, it ranked all the 4 features. Okay. Among the 4 feature, the fourth feature, pedal width is highly ranked. The rank value is 0.376. It is the first rank. The third feature, pedal length, is the second ranked feature, the second one here. Sepal length is a third, and sepal width is the fourth. This 4312 is the actual position of the feature. That is, sepal length is the first one, sepal width is the second feature, so pedal length and pedal width are third and fourth feature as per the data set. So this is how we have in the data set. So in that it ranked all the 4 features. So rank-based algorithm will rank all the features and we have to select the best subset. So you have to try it with 2 features, and also try it with 3 features and or 4 features, and try to identify the best subset. So that is how we have to do it with the ranker-based method. In wrapper-based method, in the algorithm position, we have to choose the classification algorithm. So that's all about my presentation. Any queries?
Thank you, sir. Thank you for your valuable sessions.
Madam, you can add your own data set in VK classifier. You can go to tools. So here in the VK Explorer, we have a tools option where you have ARF viewer. There you can convert them to other formats, or in the pre-process, it will allow you to open various files, CSV and JSON formats, and different formats it supports. So you can use not only even a MATLAB files also it supports. So you can use all these files in the file opening in the pre-process. When you open the file, you can choose different file formats. Except XLS almost supports other formats.
Participants, any other queries?
The correlation coefficient is used by some of the algorithm. That is, I think not the dependency. There is another set of feature selection algorithm. They use a correlation. Correlation is one of the important metric to identify the relationship between different features.
Yes, sir. That's all, sir. Thank you, sir. Thank you for your valuable session, sir.
Thank you. Shall I leave the session?
Yes, sir. Yes, sir. Thank you, sir.
Thank you.
Dear participants, okay, we have next session by 2:30 p.m.